Assalamu alaikum. After discussing the vibrational energy levels of diatomic molecule and polyatomic molecule, now we are in position to discuss the vibrational spectra. So, a vibrational spectra is emitted due to transition between the vibrational energy state. However, simple transition between the vibrational state doesn't emit a vibrational spectra. Only those transitions emit a vibrational spectra which involve the change in dipole moment. Okay, this is very important. You have to keep in mind. So if there is a transition which involves the change in the dipole moment, so the energy of the emitted photon must be equal to the difference between the energy of those states. So let's suppose the transition has taken place from the energy state M to another state N. So the energy of the emitted photon must be equal to Em minus En. When we were discussing the vibrational energy level, so we found that the vibration of a molecule behave like a simple harmonic oscillator, and there are selection rules for the transition of energies between the energies of the simple harmonic oscillator, and those selection rules are obtained from the solution of this integral. So if this integral is zero, it means the transition from M state to N state is forbidden. And if this integral is non-zero, it means that the transition from M state to N state is allowed. Here you have to keep in mind that the forbidden doesn't mean 100% forbidden. It means this transition has minimum probability. And when we say that the transition is allowed, it means this transition has maximum probability. And when we look into the vibrational spectra, so those transitions which have maximum probability are the allowed transition have intense line, while the forbidden transition have a very weak line. And we also know that while solving this integral, this comes out to be non-zero only in the case when the difference between m and n is either plus 1 or minus 1. So if we apply this condition to the vibration of the molecule, so the vibrational energy level of the molecule are represented by the vibrational quantum number. So only those transitions are allowed for the vibration of the molecule for which the vibrational quantum number changes with plus 1 or minus 1. And if there is some inharmonicity in the vibrational motion, so the selection rules are changed, and now you can have the plus 2, minus 2, and plus 3, minus 3, and so on. So it depends upon the degree of inharmonicity. If there is more inharmonicity, so you can have plus 2, minus 2, plus 3, minus 4, plus 4, minus 4, and so on. If you are at the room temperature, so we know that at room temperature, most of the vibrational energy states are at the ground state. So it means that the transition will take place from V is equal to 0 to V is equal to 1. That is why at room temperature, the more intense lines occur from the transition which takes from V is equal to 0 to V is equal to 1. However, other transition also take place, that is from V is equal to 0 to V is equal to 2, or V is equal to 3, or from V is equal to 1 to V is equal to 2. But those transition are the weak transition, or the emitted line will be a weaker line. Okay, so you have to keep in mind that pure vibrational spectra only exist for solid and liquid, because in solid and liquid the molecules are very close to each other, or they are very strongly interacting with each other, and they inhibit the rotation of the molecule. However, in case of gases and vapor, we have a mix of vibrational and rotational transitions, so we have a vibrational rotational spectrum. We know that a vibrational energy level consists of large number of rotational energy levels. So you see here, this is the ground vibrational state, and it consists of multiple rotational energy states. Similarly, This one is the next excited vibrational energy state, and it consists of multiple rotational energy states. So when there is an excitation from one vibrational level to another, it means there is a simultaneous excitation of large number of rotational energy states. That is, when we have an excitation from V is equal to 0 to V is equal to 1, so simultaneously we are exciting these rotational state to the next higher rotational state as well. So when a vibrational spectra from gases or vapor molecules do not show isolated lines of vibrational transition, but instead a large number of closely spaced lines due to transition between the various rotational states of one vibrational level and the associated rotational state of the other vibrational level. So that is why the spectral lines appear to be broad stick. We call them the vibrational rotational band. So if the centrifugal distortion and harmonicity is ignored, this we just do for the sake of simplicity, then the energy level of atomic molecule are this one. So this one is the energies associated with the vibration, and this term is the energies associated with the rotation. So that is why we represent this E by Vj, where V is for the rotation, vibration, and J is for the rotation. So we know that for vibration, we have the selection rule as delta V is equal to plus minus 1. For example, from V is equal to 0 to V is equal to 1, and we have the selection rules for rotation transition as delta J is equal to plus minus 1. So here we have vibrational rotational spectra, and it consists of three branches. One we call the P branch, and this is associated with the delta J is equal to minus 1. And we have the Q branch in the middle, and this is associated with the transition delta J is equal to 0. And we have and the R branch, and this is associated with the transition delta J is equal to plus 1. And for the vibrational transition, we have a transition from V is equal to 0 to V is equal to 1. So in this V is equal to 0, we have different rotational energy level. For example, J is equal to 0, J is equal to 1 up to J is equal to 4. Similarly, this V is equal to 1 vibrational level also consists of a transition from also consists of energy state associated with the rotational motion J is equal to 0 to J is equal to 4. So this transition from J is equal to 4 to J is equal to 3 is allowed, because here delta J is equal to minus 1, and this is also allowed on the basis of the selection rule of vibrational transition, because all these energy level correspond to the V is equal to 0 state, and all these energy level correspond to the V is equal to 1 state. Similarly, this transition from 3 to 2, from 2 to 1, and from 1 to 0, they are allowed. So for all these transitions, we have delta J is equal to minus 1, and this is the vibrational rotational spectra, and this branch is a low frequency branch. Okay, so on the left we have the low frequency, and on the right we have the high frequency. When we talk about the R branch, this is associated with delta J is equal to plus 1, and this is also the vibrational rotational line, and this is a high frequency. So here you see that here in this transition we have from 0 to 1, from J is equal to 0 to J is equal to 1. So delta J is equal to 1 minus 0 is equal to plus 1. So for all these red lines, delta J is equal to plus 1, and for all these purple line, delta J is equal to minus 1. However, for this blue line, we have delta J is equal to 0, and it means that there is no rotational excitation. The only excitation is the vibrational excitation. So this Q branch is associated with the vibrational line, and the P and R branch are the hybrid line, which are vibrational and rotational as well. So the spacing between the different spectral line in the P branch or R branch, or even the spacing between the lines of P branch and R branch could be used to measure the moment of inertia and hence the bond length of the molecule. Here, in case of the P branch, so the frequency of the emitted photon will be equal to 1 by h e j minus 1 to ej. So here, so the transition is from J4 to J3. So the difference is J3 minus J1. So that is why we are talking about J minus 1 to J. And for vibrational, it is from vibrational state V is equal to 1 to V is equal to 0. So we have this one is the rotational vibrational energy. So what we need to put different values of J and V. So we have this situation for E1 J minus 1 and this situation from E0 J. So after the simplification, we are here at this energy state. So this is the energy, the frequency of the photon of the P branch of the spectrum. We can also find the difference between the two lines of the this branch. So this is from, for example, if we talk about this one, so this is from j is equal to 3 to j is equal to 4, and this is from j is equal to 2 to j is equal to 3. So the left one is from j minus the left one is j, so the right one will be j minus 1. So the right one is at higher frequency, so we have to subtract the left one from the right one. So if we do simplification, so the difference between the two frequency line is equal to h cut divided by 2 pi I. So this is independent of the value of V or J. So it means that the frequency line or the spacing between the frequency line is the same. If we go for the R value, so this is high frequency, this is lower frequency, so you have to subtract it from J plus 1 to J. So after this subtraction, you are here at this value. So this is also the same spacing as we saw in the P branch. Similarly, we can calculate the spacing between the R and P. For example, this is the lowest frequency in the R branch, and this is the highest frequency in the P branch. So we can calculate the spacing between these two by this relation. So J plus 1 and J minus 1. So after the simplification, we have this value. So this means that the spacing between the R and P line is double of the spacing between any two lines of the R or P branch. Now, as far as the calculation of the moment of inertia or bond length is associated, so for example, the spacing between the P line is this one. So we can bring this I over here and delta nu P over here. I, we know that this is equal to mu R square, this R is equal to this one. So just if you know the value of the reduced mass and all others are constant, and this delta nu P in case of R, this is nu R, and in case of the P and R, but nu PR, this could be easily calculated. So this spacing could be calculated, this spacing could be calculated, and this spacing could be calculated. So from the spacing of these line, we can easily calculate the bond length. So these rotational and vibrational states are not completely independent of each other. There is some sort of coupling between the rotational and vibrational energy state, especially when we go to the higher vibrational and rotational state. So when there is a coupling between the vibrational and rotational state, so a term related to the vibration and rotation must be subtracted from equation number 1. So up to here we had equation number 1, and now we subtract this term, and this term is actually associated to the vibrational rotational term. So because of this subtraction, not only the space between the spectral line reduces, but they also does not remain constant, because as we go to the higher vibrational state, the spacing go on decreasing, and unlike in rotational space, when we go to the higher rotational energy level, so the spacing go on increasing. So because of the coupling, neither the space remains the same, uh, and their value go on decreasing. Similarly, we have different selection rules for the linear polyatomic molecules. So, for example, we take the example of carbon dioxide. So in carbon dioxide, we have the stretching and bending. So the stretching actually gives rise to the um, dipole oscillation parallel to the bond axis, and this is only the asymmetric stretching. When there is asymmetric stretching, so there is no change in the dipole moment. So that is why there is no spectrum associated with the symmetric stretching, only the asymmetric stretching that gives rise to the oscillation of the dipole parallel to the bond axis, that gives rise to the spectra. That is why we have a selection rules for the parallel dipole oscillation, which is associated with the asymmetric stretching. Similarly, we have different selection rules for the perpendicular dipole oscillation, which is actually associated with the bending. And when we talk about the Q branch, so there is no rotational transition associated. So we only have delta J is equal to plus minus 1 or delta J is equal to 0, the selection rule. Similarly, if we have the non-linear polyatomic molecule, of course, and the symmetric one. So here we have the selection rule for the parallel oscillation, and here we have the selection rules for the perpendicular oscillation. And of course, this parallel oscillation associated with the asymmetric stretching, and the perpendicular oscillation associated with the bending. After discussing the rotation and vibrational spectra, now we are going to discuss the electronic spectrum. And you have to keep in mind that in uh, one electronic energy level, there are multiple vibrational energy level. And in one vibrational energy level, there are multiple rotational energy level. It means that one electronic state consists of multiple of rotational and vibrational energy level. And a transition from one electronic state to another electronic state means a transition of multiple rotational and vibrational energy level as well. So we have a band spectrum, because this consists of contribution from the vibration, rotation, and electronic transition. And so the molecular spectra appear like in the form of band. And when we have a high resolution spectrometer, and if we resolve this band, so we will see that this band is actually consists of a spectral line contributed by uh, different contributed by the rotational, vibrational, and electronic transition. And one important point is that whenever there is a electronic transition take place, it takes place in a very short interval of time. That is no change in the bond length associated with the electronic transition. This was suggested by Quantum principle. So when we have to represent electronic transition, so we always represent the electronic transition by a straight line. For example, you see here on the horizontal axis we have internuclear separation. So if we have a vertical line, it means that there is no change associated with the electronic transition for the internuclear separation. So the Frank quantum principle states that the probability of electronic transition is maximum among the state of high electron probability density, and the electronic transition takes place with no change in the bond length. That is, the electronic transition is therefore represented by a vertical straight line. So here, this is the lower electronic state, which consists of multiple vibrational states. This is the upper electronic state, which consists of the multiple vibrational states. And these are the probability density curve for the electron density. So the transition from this to this is highly probable, because this is the transition from high probability density state to the high probability density state, along with the transition that take place at no change in the internuclear distance. That is why it is represented by a vertical line. So those transitions are highly favorable, will take place at no change in the internuclear distance, along with the transition from the high probability state. So that is why we see here, this is from v is equal to 0 to v is equal to 0 is more intense line as compared to the other line. Here, the high probability state exists at v is equal to 0 in the ground state, and the high probability state exists at v is equal to 1 at the excited state for the same internuclear distance. So that is why v is equal to 0 to v is equal to 1 is the more intense line. Similarly, if we go to the higher vibrational state, so the higher vibrational state are very closely spaced. They are almost continuous. So when such a transition takes place, so we see a continuous band over here. We have another phenomena of pre-dissociation, and the phenomena of pre-dissociation occur when the potential curve of the bound and unbound excited state interact. So this is the ground state, and these two are the excited state. However, this one is known as the bound state, and this one is known as the unbound state. And when there is a transition from the ground state to one of the energy state of the bound state, so there is a possibility that the molecule shift from the bound state to the unbound state even at the lower energy. So that is why this is known as the pre-dissociation. For example, if the molecule is here at the F state and the bound state, so this will not dissociate. However, if this is at the lower energy E state and the bound state, so there is a probability of dissociation. So here the molecule dissociate at energy lower than its binding energy. That is why it is called the phenomena of free dissociation, that you can dissociate or you can break the bond at energies lower than the binding energies. Here we have two interesting phenomena, fluorescence and phosphorescence. So when there is a transition from the ground state to the excited state, and if the excited state and the ground state has the same multiplicity, so there is high probability of de-excitation. And when the probability is high, so the de-excitation takes place with a small interval of time, and in large amount of energy is emitted at small interval of time, and this phenomena is known as fluorescence. However, there is another possibility that, let's suppose the ground state is the singlet state and the excited state is the singlet state, and there is a um, transition from the singlet state to the triplet state. And now the excited state is the triplet state and the ground state is the singlet state. So this transition has lower probability. It means it will take more time. So there will be an emission of energy and longer time. So there is a emission of energy. This is low intensity energy for a longer time. So this phenomenon is known as phosphorescence. So the fluorescence is a phenomenon of emission of energy in a flash of light, while the phosphorescence is the emission of dim light in a longer duration of time. So if I summarize the today presentation, so the vibrational spectra do not take place for symmetric vibration due to no change in the dipole moment. This is very important. Vibrational spectra consist of contribution from rotational spectra. Pure vibrational spectra only occurs for liquid and solid, and spacing between the spectral lines of the vibrational rotational spectra is used to calculate the bond length. Different selection rules for transition related to the stretching and bending. So the stretching is associated with the parallel dipole oscillation, and bending is associated with the perpendicular dipole oscillation. And the electronic spectra arises due to the transition between the molecular electronic energy state, and the electronic spectra consist of contribution from the vibrational as well as rotational spectra, and the electronic transition take place with no change in the bond length. So this was all about the rotational spectra, vibrational rotational spectra, and electronic spectra. Okay, thank you. Allah Hafiz.